Okay, so can I just get the next time that happens? Can you just shout out to me again, just saying that the screen has gone bad or whatever, and we'll switch over to YouTube. And you needn't worry about the recording. The recording is all through OBS anyway, so it doesn't matter which format I'm publishing on, or which format I'm streaming on. So right. Okay, so back to this image. I'm actually going to copy the image and move it into my whiteboard over here. Oops. Okay, so the important parts in this network, or in this network, yeah, here are the three different links. So over here we've got this LAN down here has got a 1 gigabit per second. Let's draw a line around that here. That's the important piece of information there, 1 gigabit per second. Here, this link here between the two routers is 1 megabits per second. And here up here again, we're back to 1 gigabit per second. So we've got three different links with three different capacities. So let's see what the question asks us. Also note, before I move on, you've got two different hosts down here, M1 and M2. And you've also got a cache, a HTTP cache here, and a DNS cache here, which are very important. Notice there's a DNS server up here, an authoritative DNS server up here as well, for our on this particular network up here, this other LAN here where B is hosted. All right, so let's see what the questions are. Okay, so we're asked to download this file here. It's at b.com from our using our browser. So so the user at M1 downloads that file from b.com. End of story. The file is 1 gigabits per second. List the sequence of DNS. So this is the question here. List the sequence of DNS and HTTP messages that are sent and received by M1, as well as any other messages that leave and enter the A.com network that are not directly sent by A.com or M1.com, from the point that the URL is entered into the browser until the file is completely received. Indicate the source and destination of each message, and you can assume that every HTTP request by M1 is first directed to the HTTP cache. And that cache is initially empty. Okay, so let's go through this very, very quickly. Okay, so the very first thing that's going to happen here, so M1 is going to type in a host name into the browser, a file name into the browser, and hit enter. So what happens then? So for example, you write down google.com and you hit enter. What happens next? So the first thing that happens is you need to translate. So this is part A, just in case anyone's wondering. The very first thing that's happened, so I just put down 1. Number 1 here is that DNS is required to translate the google.com name or whatever the file name is into an IP address. So we need to, or the server name into an IP address. So DNS, so we're going to send a DNS query. M1 sends a DNS query to its cache, to local DNS cache. Number 2, the DNS cache sends query to root server, gets back an answer where the TLD is, so that responds with address or name. Number 3, well, you know, I should have put those as separate steps really, shouldn't I? So let's just rub that out. So the root replies 4, then DNS cache sends query to TLD server, 5, TLD response, 6, DNS cache sends query to the authoritative DNS server for b.com. So I'm just going to draw an arrow here to this guy over here. DNS server sends it to this guy here. It responds with IP address for b.com. So you can see seven things have happened there already, and all we've managed to do is get an IP address. Let's keep going. So now that we have the IP address, we can send the HTTP request. I'm going to ignore the TCP connections going on here, okay? So I've asked you to do that, and if you read the question, it says just ignore all that stuff. So just HTTP, M1 sends HTTP get request to b.com now that it has its IP address. That gets first sent to the cache, so it actually sends that, to the cache, to its local cache first. So nine, the local cache will take on the responsibility of getting that local cache.
So just to let you know, we can't see the bottom right of the screen.
Oh. Let me see. Oh yeah, okay. I'll get myself out of there. Hold on. Let me go over here. So the local cache then sends the HTTP get request. So it takes on the responsibility to do it to b.com. B.com replies. HTTP message containing file. Okay, so that took a while. You can see that took a little bit of time. That's a lot of steps there. So in the first part A, if I go back to the A, the question said assume that the DNS was empty and the cache was empty as well. So that's why in both cases the DNS cache had to go and find the answer, and the local cache had to go and find the file. If they had the information already, of course, they never would have had to send. You know, the file wouldn't have to be sent at all, and the DNS would have just replied with the cached IP mapping. Okay, so now what's part B? So that's part A done. Let's go on to part B. Oh, something's gone wrong there. That screen is a bit small. Okay. So b.com sends the file. Part B, how much time does it take? And explain how you answered that. A couple of assumptions here. Packets containing any DNS commands and small HTTP commands like a get message are very small, so you can ignore the transmission delay and focus only on the propagation delay. Propagation delays within the LAN are small enough to be ignored. Propagation delay from router 1 to router 2 is 100 milliseconds. So you've got a few different things you can assume there. Let's go through it. So we've got to go and figure out the delay associated with these nine different steps. How am I going to fit this in? I should have thought of that already. Okay, I'll use red pen here. So you've got, if for each one of these cases, you've got to consider your transmission delay and your so maybe I'll do a little table over here. I'll get rid of my face here. I'm just gonna get in the way again. So let's go through 9 steps. I need to make that smaller. Propagation delay and transmission delay. So step 1, M1 sends a DNS query. So you were told that the propagation delay within the network is 0 and any transmission delay associated with a small message like DNS or HTTP GET is 0. So that's 0, 0. Step 2, our DNS message into the DNS cache sends query to the root server. So you've got a 100 millisecond propagation delay, you were told, across here. So there's 100 milliseconds here for propagation. Transmission delay you can ignore again. So this time it's going to be 100 milliseconds for the propagation delay and 0 for the transmission delay. Step 3, the root replies, same story. You're going to have 100 milliseconds on the way back, propagation delay, and 0 transmission delay with that small message. Step 4, DNS cache sends query to TLD server, same story again. You're going to have 100 milliseconds and 0, and the reply will be the same. Step 6, DNS cache sends query to the authoritative server once again. Step 7, it replies with the IP address for b.com, again that's 100 milliseconds, 0. Step 8, M1 sends the GET request to the local cache, that's just 0, 0. Step 9, oh I should have had 10 here, I'll just do 9 here, so split this into 2. Step 9 was local cache sends the GET request to b.com. Here the propagation delay is 100 milliseconds because it has to go across the network, and our transmission delay is 0. Okay, this thing's just getting in my way. How do I move it? I'm a little bit of a novice at this Surface Pro thing. So that's supposed to be 0 in here. Okay, so anyway, the b.com finally gets sends the file. So there's going to be a propagation delay of 100 milliseconds, and here we have a transmission delay now, which is just blocked for me. So I'll just do it down here with the arrow. This is the last field in the bottom right. What's the transmission delay of actually sending the file? Well, the file has a total size of, I've forgotten what it is, 1 gigabits, and your okay, that's better. So this one here is what we're calculating here. So the file is being sent here. File sent. So what do we have? We've got the 3 propagation delays would be 0 plus 100 milliseconds plus 0. That's this part here. So what's the transmission delay here? And the answer is it'd be the transmission delay for the 3 different links. 5 cents. So trans delay 1 plus trans delay 2 plus trans delay 3. So what is the transmission delay 1? So the first one is a 1 gigabit per second link up here at the top, and the file is 1 gigabits, so it's going to take 1 second there, right? So this will just be, this is just going to be 1 gigabits per 1 gigabits divided by 1 gigabits per second gives me 1 second. What about transmission delay? So that's the first one. What about transmission delay 2? That's over a 1 megabit per second link. So that's going to be 1 gigabits over 1 megabits, and that's going to be equal to 1,000 seconds. So that's that one. And then finally, trans delay 3 would be 1 gigabits per second, same as the first one. So it's just 1 second. And that's it. So you get 1,002 seconds there for that field. 1,002. And if you add up all of them together, you'll get the answer for the total delay. Does that make sense? I hope it does. I need to move on. Back to January 2019. Okay, the next part was now assume that the caches, the two, so part C and part D are to repeat the whole thing again, but this time your DNS server has the mapping you want, and your cache has the file you want. So let's go through it again. I'm not going to go through it again. I'm just going to look at this answer again and just pull out the bits that are correct now. Okay, so let's go through it again very quickly. I'll rub out the steps that are no longer true. So M1 will still send a DNS query. So step 1 is still accurate to the DS cache. This time we're not going to, step 2 will not happen. We're not going to send it to the root. We're not going to, the root is not going to reply. Blah blah. None of that's going to happen. It's just going to go straight to the DNS cache, sending it back. Oh, I missed that step actually in there. It should have been in there between 6 and 7. The cache should have replied with the answer back to M1. So I left that out, but we're going to go straight there now. So I need to delete all these guys for this case here. So what's going to happen now is we simply get, the cache will simply respond straight away. So I'll just put in a step 6.5 here. Cache replies with mapping, with the resource record, or the mapping, whatever you want to call it. Step 7, oh no, I did have that, yeah, replies. I don't know, I made a bit of a mess of that, but I hope you get the idea anyway. We just, yeah, so step 1, step 7, it replies with the IP address from b.com. Straight on here now. So next one, M1 sends the HTTP GET message to the local cache. The local cache sends a modified, because it has a cached version, so it's going to send a modified, so I'll delete that here, GET request. So it'll send if modified. So it's a conditional. On b.com then replies. I missed a few steps actually. The cache should have replied to the yeah, I missed close enough. Okay, so So the local cache will send a conditional get to b.com. b.com will just say not modified since. And then step 11, which I should have had in there, was I actually included it in the calculation down here, but step 11 would have been that the cache sends the file to B to M1, which was the 2 seconds we did down here, the translate 3, or the 1 second we did down here, translate 3. So that's pretty much what happens. The calculation is different. We lose the 1000 seconds, so this bit is gone now, because that doesn't have to be sent over the network anymore. This part doesn't have to be sent over the first LAN either. So we're just left with this 1 second delay down here. So the total today is now completely different, right? We've gotten rid of all these steps, and you can recalculate the delay, and this has changed to 1 second. And you get a new answer for D, and that's pretty much how you do that question. I'm going to move on really quickly. I know I made a wee bit of a mess of that, but I think I got all the main points across. Does anyone have any quick questions before I move on?
By any chance, do you have like the total
Do I have the total?
answer for it, just so that you can make sure in our own time we've gotten it right?
Yeah, I did this before in the previous tutorial as well, but I did it right that time, I'm pretty sure. I can remember. So if you look up the streams, yeah, you'll see it done on the light board. Okay. The main, I think I've covered the main points here in this, but if you want to get the full detailed answer, I definitely did it correctly on the light board, because I had a little bit more time. Okay, I'm going to move on. You can check that out. If you want to get access to the streams, you need to go to your teams. Go to your teams like this. I think you type in, let me just show you, I'll do it on the screen here. Go to your teams, there you go, apps. Yeah, stream is one of the apps. Click on stream. Then you need to go to, you need to click on that link on the right there. Oh, sorry, I haven't shared this screen properly. Sorry, OBS is a bit tricky. I'll go through that again quickly. So if you want to get access to the previous videos here, you go here to more added apps, find an app, one of them is stream here, click on stream. There'll be a link up on the right, Microsoft Stream. That'll access your browser and bring you to something like this. Not much to see here. Click on your groups. Click on CS320. And you'll see all of the previous ones I've done here. Let's see if I can find that one. It looks like I did it in this one here. I need to click on videos. I think it's in this one, is it? Yeah, I did this exact question, although it might be a bit small. Oh, okay, thank you. I'll try. I just you know what? I might just come out and come back in again in a second. I'm just trying to find the video for you. Yeah. Okay, I'm just going to leave and come straight back in. Hi guys, I am back. Hi everybody, I'm back. So um, if you go to that streams location, you will find, if I ever get back to it. Yeah, here. So there is I think I go through it here in this particular one. I don't know if the screen is still okay for you, but yeah, you can see me going through all the different actions, etc., and the types of messages, and I made no mistakes that time. Okay, moving on. So what is there any part of it? Does anyone have any questions about any particular thing there before I move on to a different section? Oh, okay. Thanks. Hi guys, I'm back again. Okay, so why don't we go on to TCP? So I'll give you a choice here. We can do TCP or we can do the RDT stuff. Reliable data transfer. You remember all those finite state machine diagrams? We can either do a question on TCP or we can do one of those, whichever you prefer. Yeah, okay. Okay, let's find a question on TCP. Okay, here's one on TCP. Let's go through A. So what's the purpose of the receiver advertised window or wind? Yeah, that's to let the other side know just how much buffer space you've got left in your socket. Its purpose is to avoid that socket buffer ever being overwhelmed. So by letting the other side know that you've only got, say, 1 megabit left, it won't send more than 1 megabit of data unacknowledged into the packet, into the pipe at any one time. So hence it'll just reduce down the window size so that it doesn't, so that it's never greater than the receiver buffer size. Part B, identify 6 fields in the TCP header and give a 1-sentence description of each of their uses. I mean, you've got loads of there's plenty of options here. The easy ones would be your when you've just been told to the receive window. That's one straight away. That was in part A. You've also got your port numbers for source and destination. So there's 2 more straight away. Anyone want to volunteer? 1 or 2? Nobody? What about your checksum? Checksum was another one to make sure that you don't have any errors. And of course you got your sequence numbers and your acknowledgement numbers as well coming back. So you've got sequence numbers from both sides effectively. So there's 2 more. That could bring you up to 6. And there's more as well if you want to look on. Let's go on to part 3. Consider 2 TCP sections that must share a link's bandwidth. One of the TCP connections has been running for quite some time and has built up a large TCP sending window, the second connection then starts up with an initially small window. Long term, what will be the relative throughput achieved by these two TCP connections? Explain. And the answer is they'll both get half of the link capacity. So you might remember that graphic I showed you in one of the presentations. You'll find it in one of the videos where we've got two TCP connections competing, and they iteratively converge on that diagonal line in the center, which represents half bandwidth for each of them. I can quickly show you, and it'll probably come back to you. So the idea was that this axis here would be TCP1, TCP1's bandwidth usage, and this would be TCP link 2 bandwidth usage, and the units of course would be bits per second if you're looking for that level of detail. So what happens here is at the very start we'll say TCP1 has all of it because it's already there for a while, so it's using up the full bandwidth, we'll say. So it's here. That's where TCP1 is, and TCP2 is 0. So you can see the value here is whatever, or the link capacity, and the value here is 0. Now enter TCP2. TCP2 starts fighting for some of the bandwidth. And so we get a situation. Okay. Hi guys. Does the screen look okay to you guys, or is it back to front? Is it the wrong way around, or is it okay?
It's okay.
It's okay. Okay, it's weird. From my side, it looks like it's the wrong way around. Anyway, okay. So this would be the initial situation. So immediately, OR will suffer a loss, right? Because they're both going to be trying to fight for bandwidth here, so they're going to be using more bandwidth than is available, so a loss is going to occur for the first link, so it'll immediately jump down to half its bandwidth, so to here, or over 2. And now they'll both start increasing linearly because of the way TCP works, the way it increases its bandwidth, linear increase. So they'll both start increasing from here. So I'm drawing a diagonal line because they're both increasing at the same rate, presumably. Now when they hit a certain point here where the sum of their values is greater than OR, there's going to be another loss, at which point they're going to, so a new they're going to hit a point here where a loss is going to occur, and when the loss occurs they're both going to half their values. So this one here will jump down to here, half the value here, and this one here will jump to half the value here, so they'll jump down to here. And so on, and so on. So then they start increasing linearly again, diagonally here, and then a loss will occur again once their sum is greater than OR. And the same thing will happen again. We'll go to half the values again, so it'll go to here and here. And so what we end up happening is eventually they'll just converge in the center here. The diagonal line representing OR over 2. They end up getting half the bandwidth, equal bandwidth each. So you can look up the graphic I did on the slides. It's much better than that. Alright, next part of the question. consider a TCP session and a UDP session that must share a link's bandwidth. What will the relative throughput be achieved by these two different sessions? Explain. So what will happen there, pretty straightforward answer, is the UDP will just eat up the entire thing. So the TCP session will continue to halve its window size or effective bandwidth every time a loss occurs, and UDP will just keep sending as fast as it wants. It never cares if there's a lost packet, it just keeps pumping them out, and as a result it'll eat up the entire bandwidth, and every time TCP tries to send something it'll suffer a loss, and so it'll just be starved. That's the answer. Part E, suppose we want to modify TCP so that it counts the number of segments that are lost in transit. What are the difficulties of doing this in TCP? Yeah, the real difficulty there is is that you could never know if a loss occurred, actually occurred. So you remember the ways that a loss could be identified. There was two different ways. One was a timeout, and the second was a triple duplicate. Now in either case it's possible that the packet was simply delayed. So we never know if it was actually lost or if it was simply delayed. So it's impossible, really, is the answer. So what I was looking for there was a simple discussion of that. Basically, what are the things that trigger a loss, and the fact that neither case can truly identify if a loss did occur. Okay, so that was a pretty straightforward question, I think. I'm going to take a little break here because I want to actually look at the exam paper. I've forgotten what was in there, so I just want to be able to maybe offer some more insight. So I'm going to take a little break now. I'm going to stop the recording, or pause it at least, and I'll be back in 5.
Sorry, Brian, what year was that question you just went through from?
That was 19. So the same paper, actually. So we've just been going through one paper here, yeah. January 19. Alright, I'll be back in 5.